Chemistry time, we're going to talk about limiting and excess reactants. And we're going to talk about percent yield. Both of these things are, I would say, kind of ancillarily related to stoichiometry, which just means that you have done stoichiometry. That one lesson that we did and the practices we've been doing are stoichiometry. These are examples of things we can do with stoichiometry. So limiting and excess reactants is what we did in your bell work. The equation we had was this. Sodium hydroxide plus hydrochloric acid yields sodium chloride plus water. Okay? That was our reaction. Balanced? Yep, and then your task in your bell work was to find, it said that you were given, that it yielded 59.66 grams of sodium chloride, so 59.66 grams of sodium chloride. You found the molar mass of sodium chloride. You converted from moles of sodium chloride to moles of sodium hydroxide, right? Isn't that right? Mm-hmm. All right, let me put my labels in here. You don't have to write it down. You already did it. That's okay. What's our mole ratio here? Well, this was balanced, so it's 1 to 1, which is super easy. Molar mass of sodium chloride?
1.
1 mole of sodium chloride is equal to?
58.44.
58.44 grams. Our answer was 1.02 moles of sodium hydroxide. Right? The question was, in the problem it said, with an excess of hydrochloric acid. And what that means is that we want to find how much of this reacted, and it doesn't matter to us how much of this there was. Does that make sense? In order for this equation to work out, we have to say things like, there was an excess of hydrochloric acid, because then you wrote down this very important and true principle of chemical reactions, which is what? What did you write down because of that?
Reactions can only go until one reactant is used up.
Yeah, exactly. Reactions, RXs, can only, let's say proceed, because that's like a fancy way of saying go, can only proceed until one reactant is used up. Can you guess, based on your vocabulary and the title of this lesson and this sentence, what we might call that reactant that is used up?
Sucky one.
No, sucky one is not up here.
Percent yield.
Exxon.
Which of the reactants might be the one that gets used up first and therefore limits the reaction?
The limit.
There we go. We call that, so write this down, we call that the limiting reactant. The methodology to finding which reactant is limiting is pretty simple. We're going to say what it is in a second here. Reactions can only proceed until one reactant is used up, and that one reactant that is used up is called the limiting reactant. Oh, forgot to do the picture. Picture. There we go. All right. Here's an example. It says, the reaction between solid sodium and iron 3 oxide is one in a series of reactions that inflates an automobile airbag. That's kind of interesting. You know about automobile airbags? Hopefully you don't know very much about them. It gives you the reaction. It says, if 100 grams of sodium is used and 100 grams of iron 3 oxide are used, determine the following. So, to find the limiting reactant, here's what we do. Write this down, please. The one step we have to do differently is to determine limiting reactant, comma, complete the required stoichiometry problem using each given value. So basically, you were given, from that problem I just read, 100 grams of sodium is used and 100 grams of iron 3 oxide is used. We do both problems of the stoichiometry, and we're going to get two different answers. Which one was the limiting one, if we get two different answers? The one that produced what?
The least.
Yeah, there you go. Let's write that down next. The answer that is the least corresponds to the limiting reactant. We're going to do that exact problem here in a second. But that's as simple as it is. We just do two stoichiometry problems, one with each of the givens. You see what their answers are. And the one that actually happened, the one that did limit it, is the one with the lower answer. This is just conceptual right now. We have another example problem, but you have questions about how this would be done. Can you imagine in your head doing two different stoichiometry problems? Hopefully. And then you just compare the answers. Which one's lower and which one's higher? The lower one is what actually happened because it was limited by that thing. So if we found that reactant A was lower when we do these two stoichiometry problems, then A is the limiting reactant. Not only is A the limiting reactant, but how much was actually made? Whatever the answer for A was, right? If we get two answers and one's 12 and one's 13, 12 goes with the limiting reactant, and we obviously can't have made 13 if 12 is the lowest one. You all have this written down?
Yes. Correspondence.
Corresponding.
Corresponding.
Corresponds. I don't know. I can't. I'm going to erase what's up here then, and we're gonna perform the practice problem that I just read to you. So write down your given. Your givens are 100 grams of sodium and 100 grams of iron 3 oxide.
What's this off of?
This is I'm on page 383. I'm looking at problem 22. Yep.
What is it again?
So our equation is this. 6Na plus Fe2O3 yields 3Na2O plus 2Fe. Sodium plus iron 3 oxide yields sodium oxide plus iron. Given 100.0 grams of sodium and 100.0 grams of iron 3 oxide, find limiting. Our first responsibility is to find what the limiting reactant is.
100 grams of.
Then we're going to find the excess reactant. Let me ask you a real simple question. If we find the reactant, if there's two reactants, A plus B yields AB. If A was limiting, which one was excess? B. There you go. It's just the other one. And then it'll say the mass of excess reactant that remains. And then we're going to talk about how to do that, but we need to find then, mass of iron produced. And we need to find the mass of excess, mass in excess of the excess reactant. I abbreviated excess reactant ER. In this case, ER does not stand for emergency room. Sometimes ER stands for emergency room. In this case, it stands for excess reactant. What do I do first? You should know this part, right? It says, to determine limiting reactant, compare the required stoichiometry problem using each given value.
Okay, so you go.
What should I do first for my stoichiometry problem?
No,
It's balanced. Good. Yes, thank you.
You're
Zoe.
gonna
Now
find
you-
your molar mass.
Find the molar masses. What molar masses am I going to need?
Sodium
Na.
and Fe.
So sodium is going to be easy. Na equals 22.990 grams per mole. For Fe2O3, it's going to be a little bit harder. I know oxygen, 15.999 grams per mole. Iron is 54 point something? No, it's
55.845.
0.845
Times that times
grams
2
per
plus
mole
15.999
times 3
times 3.
equals.
159.687.
Does someone concur?
You did that fast, Tylee.
Okay, well, someone else do it even a little bit slower so we can have a concurrence. Does someone, you know what concur means? Like, do you agree? Does someone else have that answer and they agree that it's correct?
Slower. Yes.
Good, thank you.
No.
Now here's the thing. What are we going to go to? Eventually we need to find the mass in excess and we need to find the amount of iron produced. But does it matter which one of these two we use? Nope. Because if we convert both to sodium oxide, now you need to remember this. Maybe you're right, no, but you need to remember this. Because it's going to, at this point, you're going to say, I don't know what to go to, right? If you don't have me up here saying, telling you what the next step is, you're going to have a hard time finding it. Go to either one, as long as what? What's going to be the requirement? Go to either one, but make sure that you go to the same one for both, okay? In this case, we could go either convert both to moles or mass of sodium oxide, or we could convert both to moles or mass of iron. Looking at our finds, what would be the best one to do? Because we'd get two birds stoned at once.
Iron.
Yeah, probably mass of iron, because one of our requirements for C is to find the mass of iron produced, okay? So let's do that one. What should I do now?
So you take, grains.
We're given 100 grams of sodium and 100 grams of...
So which one do you want to do first?
Let's do
Sodium.
this.
100 grams of sodium, and we're converting to what?
Mass.
Of
iron.
mass of iron. So, first step, if we're going from grams to moles, grams of sodium to moles of sodium.
2.9.
Grams of sodium.
And then, no, let's do we always want to do our units first. Moles of sodium to moles of iron.
Yeah.
And then moles of iron to grams of iron. We're also going to need the molar mass of iron, which we already happen to have up there, 55.845 grams per mole. Ooh, nice. This is looking swell. Let's put in our numbers. In 1 mole of sodium, how many grams are there?
And
22.99.
Yes, the molar mass. What's our mole ratio here?
6 to 2.
Well, let's say it the better way.
3 to
2
1.
to 6.
2 to 6, because the
Oh.
iron's on top, so I'm going to put 2 on top here. 1 to 3 will work fine, Ty. You said 2 to 1. That won't work. Just what I would do, don't worry about reducing this. I don't really care about that at all. Just plug in the numbers from the balanced equation there, the coefficients from the balanced equation there. And then for our, in 1 mole of iron, there are 55.845 grams. 2 people do this, at least 2 people, so that I can have a corroboration. I mean a concurrence. In the meantime, just to save time on the video, I'm going to set up the second one.
You get it?
Right there.
Okay. What'd you get?
I'm waiting for someone else's. I got 80.97.
Give me 1 second, please.
Yeah. Nice.
Say it again, Ty.
80.97
No, 80.97 what?
grams of iron.
Good. Someone else concur?
Ace can.
Okay, good. Now do the second one. I've just set up, so now we're doing the same thing except we're converting from grams of iron 3 oxide, which I put here on the bottom, of course, use a different mole ratio, and then we're converting to grams of iron. What am I missing here?
Heart. On both of them.
Oh, double heart. Rare double heart. Like it's got 2 hearts. Octopus?
Cow?
I think not, Ty. That would maybe somewhere in the world, but I don't think normally.
Teddy, you remember learning about that? About what? In Miss Cooper's? About the
I think octopi might.
systems.
Octopodes.
and how
We don't say
they-
octopods.
Not us,
Octopodes
but like
might.
other
We're gonna
things.
have, after the video's done being, after the video's done being filmed, I'm gonna give you guys a lesson about
Yeah,
why we don't say octopi.
or kind of, there's a couple more.
Why do we say
animals
cacti? then?
on land.
Because that's a Latin word, and octopus is not. We're gonna get to it, Ty, I'm telling you.
Okay.
Okay. I'd love to have someone besides Ty and Hayes do this one, just so that we all get a chance.
I did the last one too.
Oh, good. I'd like to have someone besides Ty and Hayes say them aloud. I'm gonna put in some elevator music in this part of the video.
Did somebody else do it?
Mm-hmm.
I'm the only one that has done it.
That's okay. Good job, Natalie. You win.
Yay, do I get a sticker?
Okay.
5, I would have used 55.
I'm just maybe we'll see. It does mean 55.845.
It's 69.94
69.94 what?
grams of Fe.
Does someone corroborate? I mean, does someone concur? Corroborates the same.
Let's go calculate.
They're pretty similar in value, right? If Natalie's right. If Natalie is right, which of these was the limiting reactant?
This one, the second one.
The
You got
iron
what?
3 oxide.
69.94. That's what I got.
Thank you, Tyler. Okay, so since 69.94, you remember kindergarten. Since 69.94 is less than 80.97, which we know because of the way numbers work, which of these is the limiting reactant?
Oh.
Iron 3.
So now we know, this is our answer to A. It says, what is the limiting reactant? This is the limiting reactant. The limiting reactant is iron 3 oxide. What is the excess reactant?
The other one.
The other. So this one is limiting, because it's less. This one is excess, because it's more. How many limiting reactants? There can be more than 2 reactants on the side. How many limiting reactants do you think we can have?
One.
Just one. Just one determines how much of the product can be made. Then how many excess reactants do we have?
Equal.
The rest.
The rest. It doesn't matter. In this case, it's 1, but the rest of them are in excess. Unless they're completely equal. And then that's what we call perfect stoichiometric ratio. You might remember one of your bell wishes at the very beginning said they react in a perfect stoichiometric ratio. And you all were like, what does that mean? I can't do it. I don't know anything. Remember that? The perfect stoichiometric ratio just means that these would come out to be exactly the same.
I got it.
Do you see what I mean?
Yep.
Okay, time.
Ugh.
Now it says mass of iron produced. So what mass of iron was actually produced?
80, no.
Try again.
No, it's 69.
69.94 grams of iron was actually produced. Why?
Because it's your limiting.
Because it was the limited one. And now we have to find the mass in excess. Here's where we have to do another piece of math. So this one, and this will be on your test, the mass in excess, what we do is we take the amount that we actually needed. Either we can use the limiting reactant, or we can use the find that we found here. But then we're going to convert that to the excess reactant.
So
Do you see why? We're going to find how much of the excess reactant was actually used.
why can't you just subtract them?
You can't, because that's not how it works. Because you can't subtract, this just doesn't, it don't work. It don't work, trust me. Now write this down. To find the mass in excess, to find the mass in excess, convert the limiting reactant, oops, spell it right at least, reactant. Oh, I did spell it right, now I spelled it wrong.
Oh.
All right. Reactant, or found value to mass of excess reactant. So we're going to do another stoichiometry problem, this time converting from either this or this, doesn't matter, to the other. And what that'll give us is how much of the sodium in this case was actually used. And then, and only then, can we do what? We're going to take the answer we just got, which is how much of the sodium was actually used, and subtract it from what?
You just said we couldn't subtract it.
Yeah, but now, whatever, let's just go on. So let's do it. So we have, what's our limiting reactant?
Our limiting reactant is 69 point...
No, that's not the limiting reactant. What's our limiting reactant?
Iron.
Iron 3 oxide is the limiting reactant. So we're going to take our given of the limiting reactant, 100.0 grams of iron 3 oxide, and now we're going to convert to what? Our goal is to convert to, I just told you. I just wrote it. To mass of the excess, right?
Yeah.
So now from grams of iron 3 oxide, we're going to go to what?
Grams of iron.
From iron 3 oxide to
Grams of that.
Grams of iron trioxide to moles of iron trioxide.
Thank you. And then?
Moles of iron trioxide to moles of... what are they?
Exactly. See, this is where I'm telling you, you're going to get tripped up. But what are we trying to convert to here? We just said it now.
Excess of the excess, so that is iron?
No, what's the excess?
Oh,
right?
sodium.
Sodium. So
Okay.
we're going to convert to moles of sodium. And then, from moles of sodium to
Moles of... or
No.
grams of sodium.
grams of sodium. Thank you. Let's put our numbers in. In 1 mole of iron trioxide, as we know, there are 159.687 grams of iron 3 oxide. What's the ratio of sodium to iron 3 oxide? 6 to 1. That came from the balance formula. And then in 1 mole of sodium, there are 22.990 grams. You see where all those numbers came from? So what will this actually tell us? This will actually tell us how much of the sodium we needed for this reaction to occur. We're about to find out. 108 point.
Oh, I did not get that.
You can't. I don't think that can possibly.
I
happen.
got 86.381.
86.381. I don't know exactly what went wrong with yours, Hayes.
I got 86.381.
So 86.38 because we were using sig figs, and it's grams of sodium. Now we know. What does this tell us?
That's what
the
you
actual
use.
excess?
This is how much we actually used of the excess. How much did we give it? 100 grams. How much did we actually
Now
use?
we have to
86.38. Now we have to.
Subtract.
Now we have to subtract
86. Well, 80.
100.0
100.
grams of sodium minus 86.38 grams of sodium. Bye-bye. Bye-bye. Equals. So remember, we're trying to find how much in excess there is.
13.62
13.62 what?
grams of sodium.
Grams of sodium. So then, now think about it. When this reaction happens in the automobile airbag, that means that we're going to have 13.62 grams of sodium left over. How much of this is going to be left? Iron 3 oxide. None. It's gone. It's used up.
Mr. Connie,
There's going to be 13 grams of sodium.
Just of sodium and you need your heart.
Yeah,
You literally stress test how important.
This is a good heart, Ty.
You need this heart, and you were slapping on the board and everything.
Okay, let's move on real quick. Do you have questions about this specific? We're going to do more practice, but do you have specific questions about how this is done? Let's hear them, Kylie. I don't get it as not a specific question. Do you have questions?
I didn't say I didn't get it.
Do you have questions?
No.
Okay. All my erasers are on the ground.
I wonder why.
I don't know. Okay, now let's move on real quick. We're going to do percent yield. This one's quite a bit, I would say, easier. So write this down, please. Percent yield. And then we're going to write down the basis of this real quick. So in a sentence, write percent yield is, start out with that. Percent yield is a comparison. Too fast?
Yeah.
Percent yield is a comparison Percent yield is a comparison of good.
Yeah.
Percent yield is a comparison Percent yield is a comparison of the amount of a product actually produced. Whoops. And the theoretical amount, I'm going to put in parentheses here something in a second, theoretical amount produced. Percent yield is a comparison of the amount of a product actually produced and the theoretical amount produced. Very simple equation for this. There's a very simple, yeah, we're going to talk about it in a second. There's a very simple equation for this, which is this. Write this down, please. Percent yield equals actual yield over theoretical yield times 100%. You use this equation quite a bit in your life, you don't even realize it. Where else have you seen this equation?
Never.
Not never.
Once in math before.
No, you're wrong. Every time I give you a grade on your test, it's this. It's your actual score divided by the theoretical score you could have gotten if you'd been better, right? Times 100. So if you get a 60 out of 80 times 100 is 75%, right? Listen. Let me say it again. If you get maybe a 10 out of 20, right? There are 20 points possible. You got 10. That's 0.5 times 100 is 50%. You use this all the time. So all it is comparing how much you actually got from a reactant or from a reaction to how much you theoretically could have gotten. How do you theoretically determine how much of the reactant could have, or the product could have been produced?
the amount of points you put on there.
Okay, so in the test, yes. But for this, for chemistry, how do you determine the theoretical amount that could be produced?
It tells you.
How much you have.
Sometimes they'll tell you, but you do the stoichiometry. So I'm going to put this
Oh,
here. The theoretical stoichiometric, I'm going to put in parentheses, yeah.
That's not good.
Yeah, it does. Stoichiometric. So you do, to find the theoretical,
How
you
do you
do
spell that?
stoichiometric. You do stoichiometry. Your actual will be given. Listen to me, please. Your actual will be given in one of two ways. Either you will actually find it in the lab, right? Like you'll do a reaction, you'll find a certain mass at the end. Or it'll be given to you from your book. If you're doing a problem, it'll say, Becky did a lab and she got 10 grams and she should have gotten, and you'll calculate how much she should have gotten, and then you'll say, what's her percent yield? So you do the stoichiometry, as we've been doing stoichiometry, to find the theoretical. Relate those two things in your brain. Theoretical yield and stoichiometric yield mean the same thing. You do stoichiometry to find the theoretical. The actual will be given either by you doing a lab or by the book will just give it to you. So look at this. That one won't work. Look at page 386 with me, please.
386.
.386 reads, and we're not going to do this all in work because we don't have time, but it says percent yield, 386. I'm in a box that says example problem 11.6. Do you see that?
Yeah.
I'm going to read it aloud. Solid silver chromate forms when potassium chromate is added to a solution containing 0.5 grams of silver nitrate. Determine the theoretical yield of silver chromate. Then calculate the percent yield if the reaction yields 0.455. Look, if the reaction yields 0.455 grams of silver chromate, what's your actual yield? It just gave it to you. 0.455 grams of silver chromate. So then to find the theoretical yield, it says, determine the theoretical yield. That's just doing the dang stoichiometry, right? So you're going to convert from, and they show you this, but you convert from 0.5 grams of silver nitrate, which is given. Just do the normal stoichiometry to find how much silver chromate. And look a little ways down the page. How much silver chromate is found? Or do they get?
How do you...
0.488 grams of silver chromate is the theoretical yield. So then all they do is they take 0.455, which was given, oops, CR. Is it CrO4, is that what it says?
Divided by
AgC2.
.488.
Do you see how these things line up? Because this was given as the actual yield from the book. And then you would have done stoichiometry if we had more time. We would have done stoichiometry with this. And they just divide them and then multiply by 100%, and you're going to get some value, which is?
It's going to be, it's 0.932, but times 100 be...
93.2%. What's the unit?
I was close.
Percent is a unit, right?
Yeah.
Grams of silver chromate drops out with grams of silver
What did you
chromate.
put as your answer?
93.2%.
Oh, I didn't know if you put this one.
93.2%. Yeah, we still use sig figs for the percentage.
Oh, I didn't know if I said it.
Questions about percent yield?
We're going to have to go over it more tomorrow.
You're going to do more practice tomorrow. We're not going to go over it again. You're going to do more practice tomorrow.